Yeah, welcome learners. I am Pawan Kumar, Assistant Professor in Mathematics, School of Sciences, IGNOU. So in this today we shall discuss about some concepts in graph theory. I hope that you are studying well, and in the previous session we have introduced the course graph theory, and we have given some basic concepts of graph theory. Now we shall discuss some more concepts in this context. Specifically, we shall talk about what we mean by a walk, what is a path, cycle, circuit, and then how these concepts are related to the concept of connectedness and components. So we start with there is some technical problem. Learners, that there is some technical problem. As So I would like to start with the concept of walk. So let's start with this graph. This graph has 6 vertices, namely V1, V2, V3, V4, V5 and V6. Let's start a walk in this graph from the vertex V1. From the vertex V1, we go to vertex V3 via the edge E4, and then from V3 we go to again V3 via the loop E5, and then from V3 to V4 via the edge E6, and from V4 to V6 via the edge E8. So what we have constructed here is a sequence of vertices and edges, and this sequence has the property that the vertices and edges occur alternately. You can think of this graph as a map of some city, and where the vertices represent the places and the edges represent the roads or streets. So walking in the city means you are walking from one place to another. So here, walking from one vertex to another. Of course, this walk must be completed only through some edge, right? We cannot jump from one vertex to another, that without any edge. So those vertices should be adjacent. So from V1 to V3 we have used edge E4, and similarly from V3 to V6, V3 to V4 we have used the edge E6. So such a concept gives the concept of walk, and let's now define what we mean by a walk formally. A walk W in a graph G is a sequence V0, E1, V2, V1, E2, V2, E3 and so on, EK, VK, such that for each I between 1 and K, the vertices Vi minus 1 and Vi are the endpoints of I. Note that every walk begins at a vertex and ends at a vertex. So, for example, in this walk V0 is the first vertex of this walk and Vk is the last vertex. So V0 and Vk both are called the end points of W. Let's consider another walk. This walk starts again from V1 and ends at V2, and it just goes through the sequences like the sequence of vertices and edges V1, E4, V3, E5, V3, E3 and then V2. Now we shall look at some types of walks. There are mainly two types of walk. A walk that contains no repeated edge is called a trail, and a walk that contains no vertex repeated, of course except possibly the first vertex, is called a path. That means a trail, in the sequence representing a trail, every edge appears exactly once, and in a path every vertex appears exactly once except the first vertex, which may be repeated or may not be repeated. For example, let's look at two walks shown here, W1 and W2. In the walk W1, we can see that the vertex V is repeated. That means we have gone from U to V, and then from again V to we have reached V via the loop E3. So the vertex V is repeated here, but you can see that no edge is repeated. Every edge appears exactly once. So this is a trail. Now look at the walk W2. In this walk, we can see that no vertex is repeated. Every vertex appears exactly once. So this walk is a path. Now a natural question arises that what is every path a trail? The answer is yes, because a path is a sequence of vertices and edges, an alternating sequence of vertices and edges where no vertex is repeated, right? And no vertex repeated means no edge is also repeated, because an edge is repeated only when its endpoints are repeated. So every path is a trail. What about the converse? That means, is every trail a path? The answer is no. We can see several trails which are not paths. One such trail is shown here. Look at this trail. It starts at V1 and goes through the edge E1, vertex V2, and then edge E2, vertex V3, edge E3, and then it comes again at vertex V2, and finally it reaches V4 through the edge E4. So no edge is repeated here, right? Every edge appears exactly once, but the vertex V2 is repeated. So this is a trail which is not a path. Now when the graph is simple, there is simple way of representing a walk. We shall just use the sequence of vertices only, because we know that in a simple graph there are no loops and no parallel edges. So between every pair of vertices there is at most one edge, and that edge can be represented by just its endpoints. So in a simple graph we shall simply write a walk by its sequence of its vertices. For example, look at this graph. In this graph we have this walk V1, V2, V3, V4, V2, V1. That means it starts at V1, goes through V2, V3, V4, again comes back at V2, and then finally ends at V1. So you can see that the edge V1, V2 is repeated. Of course, the vertex V2 is also repeated. So you can see that this is an example of a walk which is neither a trail nor a path. Now we shall look at another type of walk, and that type occurs due to its endpoints. That means whether a walk contains whether its endpoints are same or not. So when a trail has both its endpoints equal, that means the endpoints are the same, then that is called a circuit. And when a path has the same endpoints, then it is called a cycle. We shall denote a path on n vertices by Pn, and a cycle on n vertices by Cn. For instance, some cycles are shown here. C1 is just the cycle, you can see here. C2 is this cycle. C3 is a cycle. This is also called a triangle, and this cycle is C6. Every walk also, there is also the concept of length associated with every walk, and length is just the number of edges which occur in the sequence. So you can see that C1 has length 1, that means it has only one edge. C2 has length 2, it has 2 edges. C3 has length 3, and C6 has length 6, and Cn has length n. And a path on n vertices has length n minus 1, because you can see that its endpoints are not the same. Now we shall look at a result related to paths and walk. In fact, this result says that every UV walk contains a UV path. Given any two distinct UV vertices of a graph G, we shall show that every UV walk in G contains a UV path. The idea of the proof is, we shall give just a constructive proof. We start with an arbitrary UV walk, and so that this UV walk contains a UV path. So let W be an arbitrary UV walk in G, and let us consider a shortest UV walk P, namely P equals to W0, E1, W1, E2, and so on up to EK, WK, where W0 is equal to U and WK is equal to V. Now, if P contains a repeated vertex, say W, then W equals to Wi equal to Wj for some I less than j. But now this means that the subsequence Ei plus 1, Wi plus 1 up to Wj of P contains at least one edge. That means it has positive length. So if you just subtract this subsequence from P, what you get is a UV walk shorter than P. But we have taken P to be the shortest, that means the path with the walk with the shortest length, the smallest length. So this is a contradiction. We have found a UV walk shorter than P, and therefore P is a UV path in W. Now we shall consider the question of when does a graph contain a cycle. The first condition we shall look at in this direction is in terms of minimum degree. Just look at these two graphs. In the graph shown in the left, you can see that the red edges form a cycle, whereas the second graph has no cycle. You also note down the minimum degree of these two graphs. This graph has minimum degree 3 and this has minimum degree 1. Now look at the graph G and H. In the graph G, you can see that there is a cycle and there is no cycle in H. Note that the minimum degree of G is 2, whereas the minimum degree of H is 1. Now consider these two graphs. Again you can see that in the graph G there is a cycle. In fact, there are many cycles, and the graph H has no cycles. The degree of the graph G is 3, minimum degree is 3, and the minimum degree of H is 1. So from these examples, it seems that if we take the minimum degree of a graph high enough, large enough, then there is a chance that the graph would have a cycle. And in fact, we shall show that we need not take the minimum degree to be too high. We just take minimum degree to be at least 2, and this guarantees that the graph would have a cycle. So this is what now we shall prove. Formally we present this result as a theorem. Let G be a graph with minimum degree at least 2, then G contains a cycle. Now to prove this, the idea is to construct a path from any vertex. We construct such a path which cannot be extended. That means a path which is inextendable, non-extendable, and then this path would give us a cycle. So let's begin a walk in G at some vertex V0. Since the minimum degree of G is at least 2, dV0 is also at least 2. Then there is some vertex adjacent to V0, and let's call this vertex V1. Again we have dV1 is greater than or equal to 2 because it satisfies the minimum degree condition. So there is some neighbor of V1, say let's say V2, which is different from V1. So thus far we have constructed a path V0, V1, V2. Now if V2 is adjacent to V0, then we have already found a cycle, right? So we have to do nothing. Otherwise, if V2 is not adjacent to any of these two words, V2 is not adjacent to V0, what happens? In that case, V2 has a neighbor, say V3, which is different from V0 and V1, right? V3 is a neighbor of V2 which is different from V0 and V1. Now we can continue this process, and suppose for any k greater than or equal to 1, let Vk plus 1 be a neighbor of Vk such that Vk plus 1 is different from all the previous vertices V0, V1 up to Vk minus 1. Now, what does this mean? Since G has only finitely many vertices, this process would terminate at some vertex, and let this vertex be Vp. Now, what does this mean? It means that we cannot further extend this path. That means all the neighbors of Vp have already occurred on the path. So, in particular, let's look at any neighbor of Vp. Let's say Vi for some I between 0 and p minus 2. Like you can see this in this picture. This is our path from V0 to Vp, and Vp, now we cannot extend this path further. So, that means all the neighbors of Vp are on this path, and let us look at just one neighbor, say Vi. Now, the walk, this one, from Vi to Vp and then from Vp to Vi, this is the required cycle. So, we have constructively found a cycle. So, this completes the proof. Now, after looking at the basic concept like walk, paths and cycles, we shall come to the concept of connectedness. We define what we mean by a connected graph. A graph G is said to be connected if for every vertices u and v there is a uv path in G, and when this does not hold, that means when a graph is not connected, we call it disconnected. Let us look at some graphs. On the graph, on the left, you can see that for any pair of vertices, there is a path. You choose any two vertices, there is some path that joins them. However, on the graph in the right hand side, you can see that the vertex V is not connected to any vertex on this cycle. That means there is no path from V to the remaining vertices. So, this graph is not connected. Now, we shall look at some conditions that guarantee connectedness of a graph, and in this direction let us first look at this lemma. It says that let G be an n vertex simple graph, and let u and v be two non-adjacent vertices of G such that du plus dv is greater than or equal to n minus 1. Then nu intersection nv must be non-empty. So, what precisely it says that you choose any two non-adjacent vertices u and v in a n vertex simple graph G in such a way that their degree sum is at least n minus 1, then they have at least one common neighbor. This is very crucial result, and we shall now prove it. The argument we shall use is by the proof by contradiction. So, we shall start assuming that u and v have no common vertex. That means nu intersection nv is empty, and then we shall reach at some contradiction. Okay. So, we are given that du plus dv is at least n minus 1. Now, since u and v have no common neighbor, this means that u and v have at least n minus 1 neighbors in all. Note that du is just, when the graph is simple, du is just the number of neighbors of u, right. Similarly, dv is the number of neighbors of v. So when du plus dv is greater than or equal to n minus 1, this means that u and v have altogether at least n minus 1 neighbors, and all these neighbors are distinct because of this condition, nu intersection v is empty. Now we are also given that u is not adjacent to v. This means that these neighbors that we have found do not include u and v. So we have n minus 1 neighbors of u and v, excluding u and v, but G has exactly n minus 2 vertices apart from u and v. So this is not possible, this is a contradiction, and hence nu intersection nv must be non-empty. Now we come to the result. It says that let G be an n vertex simple graph if delta G is greater than or equal to n minus 1 by 2, then G is connected. That means if G is an n vertex simple graph with minimum degree at least n minus 1 by 2, then G must be connected. So to prove this result, what essentially we have to do is we just pick any two vertices and so that those vertices are joined by some path. That means there is some path that connects these two vertices. So let's start the proof formally. Pick any two vertices u and v. If u and v are adjacent, it means that the edge uv along with its endpoints forms a uv path. So we are done. On the other hand, if u and v are not adjacent, then the condition that minimum degree of G is at least n minus 1 by 2 implies that the sum of the degrees of u and v is at least n minus 1, right. But now the lemma that we have just proved implies that nu intersection nv must be non-empty. That means u and v have a common neighbor. So that common neighbor along with these vertices u and v forms a uv path. Thus this means that G is connected. Okay, now I ask some questions. Let G be a connected k-regular graph. You recall the definition of k-regular graph. The k-regular graph is a graph where every vertex has degree k. So determine G when k equals to 0. So what does this mean? G is connected as well as 0 regular. That means every vertex has degree 0. So only such a graph can only be a trivial graph. That means a graph which consists of just one vertex and nothing else. So in this case, this graph must be a trivial graph. Okay, in the second case, when k equals to 2, what can be G? K equal to 1. In that case, we know that the complete graph on two vertices must be a subgraph of G because it satisfies the conditions that we are given here. But K2 is the only such graph. That means complete graph on two vertices is the only such graph because you just add any vertex to it. The degree of the existing vertices increases, right. So in the second case, K2 is the only graph. Now what happens when k equals to 2? That means G is connected two regular graph. So such a graph must have a cycle as a subgraph, right? Because in the cycle you know that a cycle is connected as well as two regular. Now you add any vertex to it, that vertex must be adjacent to the edges of the cycle, so that increases the degree of the existing vertices. So you cannot add any vertex. So in this case the graph is a cycle. Now suppose you have a connected three regular simple graph. Is it unique? Must it be unique? The answer is no. There are several such graphs. I will give you just some graphs. For example, look at the graph K4, the complete graph on 4 vertices. It is connected as well as 3 regular. You can see that every vertex has degree 3. The second graph is this one. It has 10 vertices. It is connected and every vertex has degree 3. Can you identify this graph? This is a famous graph known as the Peterson graph. It has many interesting properties which you will study in this course. So now, after having basic understanding of what we mean by a connected graph, let's look at disconnected graphs. How does a disconnected graph look like? The disconnected graph means the graph which is not connected. So, for example, look at this graph here. It has precisely the 4 subgraphs, namely H1, H2, H3 and H4. You look at any vertex in H1, just take any vertex in H1 and any vertex in H2. There is no path between those vertices. Similarly, you took any vertex in one subgraph and another vertex in a different subgraph, then you will find that those vertices are not connected. So this gives us the concept of components. We can see that these subgraphs can be called the components. And what are their properties? These are not only connected, but they are maximal with respect to this property. That means, look at, for example, just graph H1. There is no subgraph of G that is larger than H1 and connected as well and contains H1, right? So all these graphs are maximal with respect to connectedness, hence they are called the components. Let's now define formally. Let G be a graph. A maximal connected subgraph of G is called a component of G. Let's look at some questions. Let G be a graph with exactly 2 odd vertices, then so that G is connected. Okay, so let U and V be the only odd vertices of G. Assume that G is not connected. Then what happens? There is no UV path in G, right? So U and V lie in different components of G. Now let H1 and H2 be 2 components of G such that U belongs to H1 and V belongs to H2. Now what does this mean? H1 and H2 are graphs in itself, right? They must, by the handshaking lemma and its corollary, you know that every graph contains an even number of odd vertices. The graph G has precisely two odd vertices U and V, and U belongs to H1 and V belongs to H2. So H1 must have one more vertex, right, which is not possible, and hence the graph is connected. Okay, now what happens when G is a graph with no odd vertices? In that case, must G be connected? I leave this question to you, it's easy to answer. The next question is, let G be a graph with maximum degree less than or equal to 2, then show that every component of G is a path or a cycle. So we start with, let H be a component of G. We just take any component, and since the maximum degree of G is at most 2, the same holds for H. That means the delta H is also at most 2. Let P be a maximal path in H with endpoints U and V. Maximal path means a path which cannot be extended. That means there is no larger path that contains P, right? So P cannot be extended. So P is a maximal path in H with endpoints U and V. If there is a vertex W in H but not in P, then there is a path P dash from W to some vertex of P, because H is connected. Now, every internal vertex of P already has the maximum degree 2. Internal vertex means the vertex different from its endpoints, right? So every internal vertex of P already has maximum degree 2. So P dash must be from W to U or from W to V. These are the only two possibilities. Thus, P union P dash is a path which is longer than P. Now, this is a contradiction to the definition of P. Therefore, Vp is precisely equal to Vh. That means P contains all the vertices of H. And now, if du and dv are equal to 2, then the path P plus uv, that means the path obtained by adding the edge uv to it, uv to P, is a cycle. Thus, what we have shown here is that every component is either a path or a cycle. Now we shall look at very important result about the relationship between the vertices, edges and components of a simple graph. This result states that if G is a simple graph with n vertices, m edges and k components, then m can be at most n minus k plus 1 choose 2. Now, to prove this, let us consider k components of G and let Ni be the order of the ith component. That means Ni is the number of vertices in the ith component. So, because we know that every component is disjoint from every other component, so if you just sum all the orders of all the components, what we get is the number of vertices in G. That means this sum Ni from I equals to 1 to k is equal to n, and now the maximum size of ith component is Ni choose 2, right? This is the maximum number of edges in any component with Ni vertices. Now the maximum size of G can be the sum of all these sizes of K components. That means the sum of n I choose 2 from I equal to 1 to K. Now this can be simplified as 1 by 2 summation I equal to 1 to K Ni multiplied by Ni minus 1. Now further we can write this as half and this summation as summation Ni square minus summation Ni, and which can be, now you know that this sum is equal to n, so this quantity becomes equal to half summation Ni square minus n, which is further equal to, we have just added and subtracted 1. Okay, so now this simplifies to Ni minus 1 whole square plus 2 Ni minus 1 plus 1. We have just expanded the square, and this now equals summation Ni minus I square. This quantity is equal, the first quantity that we have seen is the same. The second one, here when the summation is expanded, this becomes 2n minus 2k, right, and then the last summation becomes k, and then n is as it is. So now if you just just add these terms, you will find that this is equal to 1 by 2 summation Ni minus 1 whole square plus n minus k. And now there is an inequality which you know that the sum of the square of n numbers is less than or equal to the square of their sum. That means this quantity which represents the sum of the squares of Ni minus 1 is less than or equal to the square of the sum Ni minus 1. So therefore this quantity is less than or equal to this one. Now further we can simplify it to n minus k square plus n minus k, and taking n minus k out we get the desired number of size. That means this is the maximum size of G, n minus k plus 1 choose 2. Now let us look at some applications. What is the maximum size of a disconnected n vertex simple graph? So let us consider a disconnected simple graph G on n vertices and m edges. This graph is also known as NM graph. Let k be the number of components of G, then k must be at least 2, because a connected graph has only one component and disconnected has at least 2 components. Then by the result we have just proved m is less than or equal to n minus k plus 1 choose 2, and with some effort you can show that this quantity is just less than or equal to n minus 1 choose 2. So n minus 1 choose 2 is the maximum size of a disconnected graph which is simple and has n vertices. Now this question also gives another question. Let G be an n vertex simple graph with more than n minus 1 choose 2 edges. So is G connected? This question follows from the first question and I leave it to you. Now there is another question. Construct a disconnected simple graph with n vertices and n minus 1 choose 2 edges. This is also very easy. You just look at the graph kn minus 1 and how many edges does it have? It has n minus 1 choose 2 edges, right? And if you just take the disjoint union of kn minus 1 with a single vertex, right? A trivial graph. What you get is a disconnected graph, and which has n vertices and still n minus 1 choose 2 edges. So, learners, in this session we have seen the basic concepts like walks, trails, paths in a graph, and how these concepts give the concept of connectedness. We have seen certain conditions that give the existence of cycle or path in a walk in a graph, and we have seen the number of we have seen a result related to the relationship between the number of vertices, edges, and components of a disconnected graph. So, this is what we